All right, welcome back. Here is your chance to try these exercises. If you haven't done them yet, then let's pause it in a moment. These are all pretty similar to the ones I did. So if you're stuck, you might want to just go back and look at the examples from the previous videos. But once you've tried them all and you want to check your answers, I'll show you the answers to these in a moment. All right, so a lab receives a sample of germanium, not to be confused with geraniums, which are a kind of flower with little red flowers there. But germanium has an M in it, so it's different than geraniums. So it's also radioactive, and geraniums are not. So the sample decays radioactively over time at a constant daily percent rate. After 15 days, 200 grams of germanium remain. And after 37 days, 51.253 grams remain. So what is the daily percent decay rate of germanium, and how much did the lab receive initially? So we don't have the initial amount given. That's part of the question that they're asking. But you know how much there is after 15 days. So you can think of this 200 grams as the starting amount. And we're going to use the formula F of t equals A times b to the t minus t0. And the t0 is like the 15, and the a is going to be the 200. So the formula is going to be in the form 200 times b to the power t minus 15. But we got to find the b. And just like before, to get the b, we can use this value of t, which is 37, and this value of the result, which is 51. So f of 37 should be 200 times b to the 37 minus 15, and that should be equal to 51.253. And we want to solve this to get b, so we're going to divide both sides by 200. And 37 minus 15 is 22. So we get b to the 22 equals whatever 51.253 over 200 is. And you can raise both sides to the power 1/22 to cancel that out. And if you plug this into a calculator, we'll get 0. Oh, I forgot the order of operations. I need a parentheses around the exponent. So yeah, 0.93998. I'm just going to call it 0.93999. Okay, so that's the value of b. So we could write the formula in the form f of t equals 200 times 0.93999 to the power t minus 15. That should work here. You could check this by plugging in 37 and making sure you got 51.253. I'm going to do that. So 200 times 0.93999 to the power 37 minus 15. Yep. Close enough. 51.255, because we rounded off the base there a little bit. Okay. So yeah, that's that. That's the formula for it. But let's see, what's the question asking? What is the percent decay rate? So that means to get the percent decay rate, we have the B, which is 0.93999, but the percent decay rate is the R. So we gotta figure out what that R is by subtracting 1 from both sides. And that's going to be negative 0.06. Is R. Rounding off a little bit there, but that's okay. So that's the percent decay rate is negative 6%. After you move that decimal place over 2 places to turn it into a percent. Okay, so now how much did the lab receive initially? That would be, initially means at time t equals 0. So initially, we could find f of 0 is going to be 200 times 0.93999 to the power 0 minus 15. So we can calculate that here as well. Which gives you 506.036 initial grams. Okay, so that is a tricky one. Give yourself a pat on the back if you did that one correctly. There's a lot of little places to make mistakes there, so it's all right if you made some mistakes. That's how we're learning. So for exercise 2, here's what we have. A bank account was opened, whoops, to erase that. A bank account was opened in 2015, and it makes interest so that it doubles every 12 years. In 2019, it had $6,299.60 in it. Let's write a formula for the balance B of T in year T, and how much was in the account when it opened in 2015. Also find the growth factor B and the growth rate R. I accidentally wrote those questions twice. So let's think about what kind of formula would work here. We're given the doubling time is 12 years, and we have like a starting amount. So there's different ways to interpret what the year T is. I'm going to do it, so maybe this is a little easier to say T is the number of years after 2019, so that we can just say that T equals 0 in 2019 makes this a little easier. If you have a different interpretation of how you do the what T represents, either T equals 2019 means year 2019, or maybe T equals 4 means 2019 if you're thinking of years after 2015, all of those ways should work out just fine. But I want to do it so B of 0 is 6299.6. So the half-life is going to be, or the formula, sorry, not half-life, doubling time. The formula, when you're given the doubling time, is going to be B of T equals 6299.6 times 2 to the power T divided by that 12. And yeah, plugging in T equals 0, you can check, gives you 2 to the power 0, which results in what we want there. And if you're going to plug in T equals 12, you'd get 6,299.6 times 2, 2 to the power 1. So that's going to make it double every 12 years. So this is a perfectly good formula for part A. And you might have had something a little different. Now, how much was it opened in 2015? Well, this is 4 years before year 0. So for this question, 2015 is going to be represented by t equals -4, because that means 4 years before 0. So the formula still works. B of -4 is going to become 6,299.6 times 2 to the power -4 over 12. And let's calculate that here. It's going to become $5,000 if you round that up to the nearest cent. So that's like the starting amount in that sense. And if you did this with t is represented a different way, either the number of years after 2015 or the number of years after year 0 AD, then you'd be plugging in different numbers into a different formula, but hopefully it results in the same 5,000. Okay, so let's find the growth factor B and the growth rate R. So the growth factor B means we want to write this as B of t equals A times little b to the t. This is the growth factor that we're talking about, is that lowercase b here. And right now it's not written in that form with just the t as the exponent. It has t to the power 1/12. So the trick for that is to write that t over 12 as 2 to the power 1/12, and then that to the power t, because you can multiply those exponents to get 2 to a power, because 1/12 times t is t to the power 1/12. And so yeah, you can say b is 2 to the 1/12 power, also known as the 12th root of 2. Probably want to get it as a decimal here, which is 1.05946. So that's the growth factor. Now the growth rate R, just like in 6.2, means we want to write this as 1 plus R. So we have 1 plus R is this 1.05946. That's the value of B that we have. If you subtract 1 from that, you'll just get R equals 0.05946, which if you write it as a percentage is, moving the decimal place over 2 spots, gives you 5.946% is the growth rate. All right, so that is quite a tricky problem. This section has a lot of tricky problems, so good on you for getting through it. Let's write a formula for the function in the table. So let's see. If we want to, first of all, you think it's probably an exponential function because we're in chapter 6 where most things are exponential. But to check if it's exponential, we want to see, do you multiply by the same growth factor every time that x increases by 1? This was the check that we looked at in 6.1, I think, is that you want to know, is 96 times b equal to 76.8? And is that the same thing as if you do 76.8 times b to get 61.4? Another way of writing this is if you divide both sides by 96, is to write it as b equals 76.8 over 96. And if it's the same b that you multiply every time, we want to know, is that equal to the next one, 61.44 over 76.8? This was the way of checking to see if a function is exponential that we went over in 6.1. So that's what we're going to check here. Do all of these come out the same? 76.8 over 96 is about 0.8. 61.44 divided by 76.8 is 0.8. 49.152 divided by 61.44 is 0.8. So yeah, all of these are equal to 0.8. So you can conclude it's exponential. It's not a linear function or a quadratic function or any other kind of function. All right, so, and we got b along the way. So we know it's going to be something like f of x equals a times b, which is 0.8 to the power x. But we don't know the a, so I guess we could figure it out by plugging in x equals 2, and the result is 96. Or you could just write it in the form f of x equals a times 0.8 to the power x minus 2, because we know what the starting amount is if you think of it as starting at x equals 2 is 96. That's using the last formula here. Now, so you could write it like that. If you prefer to write it with just the power x, which you might have gotten if you did this a different way, I'm going to write this as 96 times 0.8 to the power negative 2, and then that times 0.8 to the power x, just splitting that up. And then we can figure out what this original a is here by doing this arithmetic. 96 times 0.8 to the power negative 2 is 150. All right, so exercise 4. Oh, and by the way, I should have said, with this, either of these formats is okay. You might even have a slightly different format. Whatever you get, as long as you can check that you can plug in these values of x and get the corresponding f of x's out, you should be good. All right. Whew, we are almost done with this tough section. So let's write a formula for this function whose graph is shown. What is the growth rate and the growth factor? Okay, so you can see that there's the y-intercept there. It looks something like 82 or 83 or 84 or something. I can't tell exactly. So it's not really clear, but it does give you these more exact points. We have the point here of where x is 10, y is 70, and over here where x is 80 and y is 20. So those are the ones we're going to use because you can't quite see the y-intercept. So we know it's going to be exponential, something of the form f of t equals a times b to the t. We just don't know the a and we don't know the b. So this is a little tricky because there's two things that you don't know. What if, instead of doing it this way, we thought about the 1070 as being the starting value of A. So, like the starting value. So, if we do it as 70 times b to the power, oh, this is supposed to be x, I guess, here. To the power x minus 10. Now, this one, if you plug in x equals 10, you'll get a result of 70. So, that saves you from having like two unknowns. Which makes that tricky. This way we only have one unknown, which is b. Now to find b, you can use the other point. We can say that f of 80 is 20. And that means plugging in x equals 80 into the formula should give you a result of 20. So this is the equation we can now solve to find b. So I'm going to divide both sides by 70. That just reduces to 2/7 equals b to the power. 80 minus 10 is 70. Now, to undo that power of 70, you can raise both sides to the 1 over 70 to make those exponents multiply to get 70 times 1/70th, which is basically the same thing as doing the 70th root of both sides. And let's see what that comes out to be. Looks like we get 0.98226. Is B. And so that's the growth factor. And, well, I guess, let's see, we can write the formula now. We can plug this into this formula. We do have a complete formula. We can say it's f of x equals 70 times b times, I just realized I'm at the edge of the screen. Make some room there. The formula should now be f of x equals 70 times 0.98226 to the power x minus 10. And yeah, we've got the growth factor here. Is already this, whatever the value of b is. And the growth rate, to get that, we use the fact that b is always equal to 1 plus r. So that means 0.9888226 is equal to 1 plus r. If you subtract 1 from both sides, you'll get negative 0.01774. Did I do that right? Yeah. Okay, so that's equal to the growth rate. Usually growth rates are written as a percentage, so this would be negative 1.774% is the growth rate. Okay, so that is that section. We got some tricky problems here. If you got through it, congratulations. Give yourself a pat on the back. The harder you try on harder problems, the stronger you will get, just like exercising. So good work on that. And I'll see you in the next video. We're actually going to skip section 6.6 because we're a little short on time, and go into section 7.1 next about logarithms. And good luck on the quiz today.